So when you think of a swing, which is an oscillator, a pendulum, the way you get energy into that swing, meaning the way you get the kid bouncing up and down really large amplitude, is you have to push, not with just some frequency, but you have to push with a frequency that corresponds to the swing, meaning you have to push essentially with the natural frequency. And so that's what we want to look at now when we force at a 1-to-1 frequency ratio, near a 1-to-1 resonance. So let's consider first, again, like a simple nonlinear oscillator, and we put down an explicit forcing. And as I said, we are interested in the case where the natural frequency of the oscillator is omega naught, and the forcing actually is also omega naught. Well, so if you look at it this way, and if you want to think about symmetries, then it's clear that these equations, as written down, are not invariant under arbitrary time shift. They are still invariant under time shift by one period, right? So if I have t go to t plus 2 pi over omega naught, the equations are also invariant. And so let's look at what happens if you use that and see what the action is on the amplitude. So again, of course, we say, well, y is given by some amplitude a times e to the I omega naught t plus complex conjugate in higher order terms. And the action now that's induced by this time shift is a going to a times e to the I omega naught t, no, not t, but rather 2 pi over omega naught, meaning it's just a. So this translation symmetry induces an action on the amplitudes, but it's a trivial action, as one says. It doesn't change the amplitude. And therefore, there's really no condition that's associated for the resulting amplitude equation, because the amplitude equation has to be simply equivariant until not doing anything. So you really get now an arbitrary equation, an arbitrarily polynomial. So you could have a00 plus a10 a plus a01 a star plus and so on, right? a20 a squared and all these other terms. So that is not too useful. At least it didn't reduce the equations. Now, this approach did not at all address the question how large the amplitude of the forcing is. We always imagine that the forcing is kind of weak, but at least that's in this limit, we can actually do calculations. So therefore, we also need to introduce the amplitude. And for that, it is better, again, to not use this equation with time-dependent coefficients, but rather write it again as two coupled equations. So therefore, let's just write that down. So consider amplitude. We write two equations, and so there will be an equation dy by dt equals stuff, and df by dt equals stuff. And so therefore, we will have again our expansion y is equal to a times e to the I omega naught t plus stuff, and f is equal to f times e to the I omega naught t plus stuff. And now if we look at the action of our translations, look at our translations, now we have that a goes to a times e to the I omega naught delta t, and f does exactly the same because it has the same frequency. So if we now consider our expansions, right? So we have the equation for a will be dA by dt is equal to a sum over all these coefficients a, k, l, m, n of a to the m, a star to the n, f to the k, f star to the L power. We don't need to write down the equation for f because we know it's not coupled to A. It only couples to A, but A doesn't feed back, so we don't need to do that. And so now we have simply the condition that 1, which is how the left side transforms under that phase shift or that time translation, that has to be equal to m minus n plus k minus L. So there's only a single condition among those coefficients. And so that actually means that there's not really a condition on the powers of A and A star separately, because whatever you would pick for M and N, you can always find K and L so that this equation is satisfied. And so therefore, you do recover that all powers are possible in this equation, just like we had in our previous argument. The difference is now, however, that we know that each power in A comes with a specific power in F. And so we can introduce the amplitudes of the forcing, and we can look at what is the term that is dominant in the limit of small forcing. So a low power of F can now be obtained in two different ways. Either K is equal to 1 and L is equal to 0, or the other way around. So let's look at each of these cases. So if K is equal to 1 and L is equal to 0, then we have 1 equals m minus n plus 1, meaning m equals n. And if we're looking at the lowest order terms, that would be, we could actually pick m equals n equals 0. So the lowest order term in this case would be something that has no a's in it. K is equal to 1, it just has a factor f, but no f star. So that's one term that we could have. Alternatively, we could have K equals 0, L equals 1, in which case we have 1 equals m minus n minus 1. And therefore, we have actually m minus n is equal to 2. So therefore, m is equal to n plus 2. So the smallest term here would be n equals 0 and m equals 2, which would be A star squared times F star. Let's double check whether that's right. No, it's not right. That star is too much. We have A squared, right? We have a m2 and n is equal to 0. N equals 0, m equals 2. So that's this term. So that's clearly, if this term is clearly small compared to this one, because A is a small quantity. So the dominant term would actually be this one in the equation. So that's what we therefore conclude. We say, well, the equation we expect to be the dominant equation has F as the leading contribution from the forcing. So then what other terms should there be in that equation? Well, we expect that we do want to have, as always, a saturating term for the amplitude. And it makes sense, although it's not required, that saturation is also there when there's no forcing. So we do want to have a term like in the standard half bifurcation, an A absolute value squared term, right? So we want to have an A absolute value squared term A. And there we know there's a term F, and then there will be a linear term, right? So we expect that the terms would be, these would be the dominant terms. And in other words, that means F is of order A cubed. And you see, this is now a different equation than we had in the non-resonant term, because we have a new term. We have F showing up explicitly, which means in terms of the A equation, it's actually an inhomogeneous term. There's a mistake. This is A. Previously, the f showed only up as f squared and then multiplying a. But here it's actually an inhomogeneous term. That makes a significant difference. The other thing you can read off here, which is not surprising, is that, you know, if you look back at what f and a mean, f is something that has a e to the omega naught t with it. So it has like corresponds to a Fourier mode with frequency omega naught, as does a. And you see that all terms in this equation correspond to a Fourier mode omega naught. Each of these corresponds to Fourier mode omega naught, again, because this special nonlinearity doesn't change the Fourier modes. Okay, so this is fine if we're exactly at the resonance, if the frequencies are exactly the same. So what could we do to, you know, are sort of close to the resonance, but not exactly at the resonance? Well, if yeah, let's see, if omega and omega naught are not the same, so say we're interested in a slight detuning, where omega minus omega naught is not 0, but it's small compared to 1. So how could you deal with that? The first thing to observe, which is actually a quite important aspect, is the following. Where all of the calculations we're doing, they're all asymptotic calculations in a sense. They're valid in the limit that a goes to 0. And of course, the bifurcation parameter goes to 0 in a similar fashion. But the important point is that we always are in the limit a going to 0. So if you now say omega minus omega naught is small, you have to say more precisely what that means. This can be a small number, but if it doesn't scale with a, then effectively, in terms of that asymptotic calculation, it's an order 1 quantity. It may be small, but 0.1 is not order a. 0.1 is a small number, but doesn't scale with a, and therefore it's order 1, actually. Now we know from our previous calculation that when you have order 1 difference between omega and omega naught, well, and in addition, but the difference is small, so that means essentially these numbers are either irrationally related, or I mean, they could be rationally related, like 19/18 or something like that. And we'll get to that later, what happens if you have such a high rational relationships. But essentially, you can think of that these are actually not rationally related. And we know what happens in that case. If they're not rationally related, then you do not get this term. Instead, you just get an absolute value squared here. So that's not going to be useful. That means we need to not just have this be some kind of a small number, but we need to scale it with a. It has to have a relationship to a. So how should that be? Well, a simple way to think about it is the following. I mean, I didn't write it down here, but implicitly, well, let's maybe do it with color. Implicitly, we know that we did allow this amplitude to be a slow function of time, or a function of the slow time if you want. And the same thing could be allowed for f. So if f is a slow function of time, then, well, let's go back here. Then if this is a function of slow time, then this is essentially, what is this? Well, it could be simply some amplitude f times e to the I, some capital omega t, plus I omega naught t, and you have a slightly changed frequency. At this point, we don't know how the slow time would be scaled with t, or at least we didn't think about it. We could think about it and figure it out, but it's not important right now. But we noticed that we could allow f depend slowly on time, in which case it would change the frequency of the forcing. So let's do that. Well, there's really nothing to be done, because it simply means that this f here is a slow function of time. And let me now write it out, because we need to do a little calculation with it. So what we actually have is this equation, dA by dt equals mu a plus gamma times f times e to the I capital omega t plus delta A squared A. So now you can say, well, this doesn't look so good, because now again we have an equation with non-constant coefficients, which is always, you know, never so nice. However, to rescue comes again that we have this special nonlinearity, and that this time dependence is not just any time dependence, it's just a complex exponential. So you can actually absorb this factor into A and slightly modify the equation. So essentially you introduce the following. You say A is going to be some other amplitude A times e to the I capital omega t. And when you plug this now into the equation, then from the derivative, you get a derivative with respect to the curly A, and you get down in I omega. And so the equation that you get reads then the following: d curly A by dt is equal to mu curly A plus gamma curly F plus delta curly A squared curly. And you saw I factored out the e to omega t, which canceled. And from the product rule, I get a minus I omega here. And this is now a nice constant coefficient equation. And we see that the detuning, which is this capital omega, this detuning shows up as the imaginary part of the linear coefficient. So you can say that the linear coefficient, the imaginary part of the linear coefficient, gives you the detuning between the forcing frequency and the Hopf frequency. And that's how we can actually capture near resonant behavior. So let me emphasize that again. If you want to capture something near the resonance, we really have to go to the resonant point exactly, to this higher singularity where omega is exactly omega naught, and then expand around that. That's how we get there. And then we get a fine equation that captures these things. And this equation now is already quite interesting. I'm not going to analyze it now, but the fact that we get an additional term here that's qualitatively different than the terms we had before makes a big difference in the solutions that you get there.